Thank you. Oh, yes, you can clap. You can clap. Please clap. Clap for Roberto. I saw the hesitation. Yeah. Good morning. Good morning, everyone. I'm so happy that so many people showed up. I have to say, last year I was also scheduled right after conference dinner, and that's, well, it was one of the first conferences after COVID, and people enjoyed the dinner. Let's put it that way. Anyway, so I'm really glad that I'm here. Thanks to the organizers for inviting me to talk to you about formation of stars and planets at centimeter wavelengths. In particular, formation of stars and planets in the very local Milky Way, like essentially less than a kiloparsec, which is very close for many of you. But hey, this is what I'm used to. So when we think of star and planet formation, there's this general picture. So we start with large molecular clouds of gas and dust, which gravitationally collapse until we have essentially a protostar still surrounded by a disk and an envelope, while a jet is pushing away material. Eventually, that envelope is going to disappear, so we're left with a protoplanetary disk in which the planets are forming, and eventually also that disk dissipates, and we're left with a planetary system. So that's just a very brief summary of the process of star and planet formation. And what is so nice about looking at nearby objects is that we can actually spatially resolve these different steps in star formation and evolution to see how these processes actually work. And this has really become possible due to millimeter interferometry, that we can now make these beautiful images of young protostars and young protoplanetary disks, of which I'm going to show you several examples. As with any review talk, it's impossible to review everything in 25 minutes, so I decided to focus on basically a couple of different topics and show you some advances that we've seen in the last 10 years or so, and the possibilities that we're going to have, the answers that we will be able to get with new facilities like ngVLA and SKA. So we'll talk about protostars, jets and outflows in protostars, of course, gaps in disks, a very popular topic, grain growth in disk, the dust mass budget and how that compares to exoplanets, winds and jets in disks, and finally a bit about astrochemistry. So here are a couple of examples of spatially resolved images of protostars. So as we have seen essentially in the advances of ALMA, many of these protostars are not following the simple spherical image that we had. Essentially, we are not looking at spherical cows. Protostars are complex systems with streamers, with often multiple components forming together, feeding each other. And we can study them both in the dust continuum, but also in various molecular components like N2H+ and NH3. And all of these components give us information about the process of star formation and the continuous feeding of the protostar as it is forming. One of the most energetic events as part of this process are, of course, the jets and outflows. And these are already measured in the brightest objects in the radio. For example, here this radio jet of Iris 18162. That was so these are images that were actually made with the VLA at centimeter wavelengths, and also the image here at the bottom. Oh, sorry, that was too far. Here we go. This one, yeah. And also the jets that we see over here. But also with ALMA, we are able to make images of these jets looking at shock tracers like SIO. So essentially, we are starting to get the first glimpses of spatially resolved jets in protostars that can tell us a bit about the energetic processes. However, the sample sizes are still very, very small. And this is something where ngVLA and SKA are really going to make breakthroughs where once we will be able to take images, but also simply measurements of spectral indices of larger samples in order to find out more about the origin of this radio emission and the working principles behind these jets. So as you've seen in the over here, there's this correlation between the radio brightness and the bolometric luminosity. But considering the scatter, it's still hard to distinguish between the different mechanisms that are responsible for the radio emission. So essentially, larger samples will help. A second component that we can study are the magnetic fields in the radio jets through polarized synchrotron emission. So far this has been done only for one source, the HH81 source, where it is possible to measure this polarization, which is on the order of just 1%, to derive the direction of the magnetic field. But of course, in order to understand and quantify these magnetic fields, we will need to do this for a much larger sample, which will be possible with SKA. Then other things that we will be able to do is efficient mapping of clouds and of filamentary regions where the stars are forming. And so one of the things that will be possible is, for example, the measurement of separations in multiple systems, multiple protostellar systems. With the ngVLA, we will be able to measure that down to only a few AU, where the current limit of the separations is on the order of 40 to 50 AU. Sorry, down to 15 AU, but with rather large uncertainties up to 50 AU separation. So essentially, by measuring protostar multiplicity down to much smaller separations, we can actually link that to what we know about multiple systems today. Then in terms of mapping molecules like ammonia, which is a very good tracer at 24 gigahertz, it is already possible to do this with current facilities, but it takes essentially 100 hours to make a map of sort of a 10 by 10 arc minute mosaic. Well, with the ngVLA, essentially we'll be able to do that in only 10% of that time. So we will be able to do this kind of mapping much more efficiently and for from much larger samples. Okay, then moving on to the disks. I always like to start with this very famous picture of the HL Tau. This was the first image that was made with the highest angular resolution with ALMA, revealing that a protoplanetary disk is actually not smooth, but consists of these many rings and gaps in the dust distribution. And essentially, this is the picture with how it started back in 2015. And this is essentially where we are now. Many disks, dozens of disks, have now been spatially resolved with ALMA at this high angular resolution. And many of these systems indeed show gaps and rings as well. And we see this, for example, in the D-sharp large program, which was a survey specifically aimed at resolving disks that were thought to be full, that were thought to be smooth, showing all these kind of rings and sometimes also substructures like clumpiness. And then more specifically, the so-called transition disks, which were already known to have large inner cavities, but also with those cavities, as it turns out, there is a lot of variety, where some of these systems have multiple gaps and rings. Some of them have asymmetries, etc., etc. So there's really a lot of substructure in disks in the dust continuum that we're still trying to understand. In fact, with the study of protoplanetary disks, we were also able to go take images of the younger embedded disks that were still surrounded by the envelope. And at least in the millimeter continuum emission, it is possible to make images now of these embedded disks. And also there, we see these gaps and rings. So here are just a couple of examples from a long list of references, showing that this is something, whatever is causing these gaps is already happening at the early stages. And well, in order to explain what is the origin of these dust rings, I do have to explain to you a very basic concept in dust evolution in disks, and that is the concept of radial drift. So if we imagine a smooth protoplanetary disk made of gas and dust, there is naturally a pressure gradient from the inside outwards. Because of this pressure gradient, the gas in the disk is not moving Keplerian, but a tiny little bit slower. It feels this additional force. The small dust grains that are coupled to the gas will also move sub-Keplerian. But whenever a dust grain grows to a slightly larger size due to collisions, it becomes decoupled from the gas. It doesn't feel the pressure gradient anymore, and it wants to move Keplerian, right? Because it just feels the gravity of the star. However, it is surrounded by all this slowly moving sub-Keplerian material. It experiences this as a headwind and therefore loses angular momentum and drifts inwards in the direction of the star. So this concept is called radial drift. It was already figured out in the 70s, long before we had ALMA or any millimeter interferometer for that matter. And essentially this was considered a problem for planet formation, because this effect happens on really short timescales and essentially prevents dust grains from growing beyond a millimeter in size. So how would you ever be able to grow to a planet if you cannot even grow beyond a millimeter, right? So this is the so-called radial drift problem. A consequence of this whole gas-dust interaction is that large dust grains always move in the direction of high pressure. So this is a little bit counterintuitive, but it is because of this, these multiple effects. And if you think of that, like say that you had something like a high pressure region in the outer part of the disk, you would be able to trap the dust particles there and they would stay there. And well, how could you create such a pressure bump, a pressure maximum in the outer disk? Well, by growing your first planet. So as soon as you formed your first planet, it will carve a gap in the disk, and at the outer edge of that gap, you naturally get a pressure bump where the dust grains will concentrate. So this is called a particle trap or dust trap, and this is a way that we're now understanding all of these dust rings and also dust asymmetries in many of these ALMA disks. However, I'm sure you realized the problem here. If you need a planet to create a dust trap, but you need a dust trap to grow dust grains to a planet, yeah, you essentially create a chicken and egg problem. And this image I already used 10 years ago when I was first presenting the dust trap images of ALMA cycle 0 data. We still haven't solved this problem. Essentially, we still don't know how we can form that first planet that then enhances planet formation. So this remains a big issue. And this is something that we hope, of course, that with more observations, maybe centimeter observations, with the ngVLA, we will be able to solve. So one of the things that we can do is studying the grain growth in disks. So this is a way where a method where we use multi-wavelength analysis, spectral index analysis, to say something about the grain growth in these various dust traps. So if we have multiple wavelength continuum observations, we can essentially disentangle surface density, temperature, grain size, optical depth, and model them all together, removing degeneracies, and get a fit or a best fit for the maximum grain sizes in protoplanetary disks. And at the moment, it looks like millimeter grains really are present in these disks. So something is going well. But there's still a major issue with the optical depth of the millimeter continuum, because with even more, essentially even more wavelengths. This was a study where they used 9 different wavelengths, including VLA images of one of the brightest protoplanetary disks that we know. What they found is that the optical depth, especially in the inner part of the disk, is still fairly high. Like at a millimeter wavelength, it can go up to 10. Like it's completely optically thick. But even at 9 millimeter, which is the bottom purple curve here, the tau is essentially close to 1. So overall, ALMA observations and even sort of longer millimeter observations are limited in what we can constrain from the data. They're optically thick. We wouldn't be able to see small density variations because of that optically thick limit. And this is something where going to longer wavelengths, going to centimeter wavelengths, is really going to help, because, well, the longer the wavelengths, the more optically thin you will be. And these are just some of the predictions that have been made for substructures that we're hoping to find with the ngVLA at centimeter wavelengths, essentially showing very small gaps very close to the host star, based on planet-disk interaction models, and also substructures of these asymmetries that we will be able to resolve. So it's a combination of the higher angular resolution, but also the optically thin emission at VLA wavelength that will allow us to do this. We will see a lot more of this in the talk by Robin Dong later today. Then another thing that is another big question in protoplanetary disk studies is the dust mass budget. How much dust mass is essentially present in the various stages of the protoplanetary disk? And how does that relate to the amount of mass that is present in exoplanets, in exoplanet cores? And so it was already realized a couple of years ago that if we look at the total mass as a function of stellar mass for disks and exoplanet cores, that the dust mass in disk is essentially below the typical dust mass in exoplanets. And there's been some discussion, there have been some follow-up studies where they say, well, maybe there are some uncertainties, but yeah, essentially it looks like whatever dust is present in the protoplanetary disk, it's not enough to create exoplanets anymore. So again, exoplanets must form before this stage, essentially in the first 1 million years. And we can try to tackle this by looking at how does the dust mass actually evolve as a function of time. And we do that by looking at the dust mass cumulative distribution, which we see over here. This is the dust mass distribution for various star-forming regions, ranging for sort of 1 to 2 million years down to the older regions of 5 to 10 million years. What you see is that the dust mass decreases over time. The dust mass here is calculated by this relatively simple equation, so just the flux scaled with the distance, and then the dust opacity and the temperature. But one of the big questions here was always like, yeah, why does this dust mass decrease? Is this actually the disk becoming less massive? Or is this a change in the dust opacity, which is this kappa value over here? And so this was some initial work was already done with the VLA by Lucas Tikhonich, who noticed that you do have this decrease in dust mass in ALMA wavelengths, essentially from class 0, class 1 to class 2. But you also see this decline when you go to VLA observations at centimeter wavelengths. It is clear from this comparison that the ALMA observations of the embedded disks are very optically thick, like the centimeter observations give much higher dust masses in these early stages. But in the protoplanetary disk stage, we're pretty much okay. So indeed, there is an effect of the dust opacity, but by the time we get to the protoplanetary disk stage, we are essentially optically thin enough to measure dust masses. And the optical depth is only high in the very inner part of the disk, but this is not dominating the total disk mass. So, but this experiment made clear that how important it is to get centimeter observations, centimeter continuum observations. Even if we don't spatially resolve the disk, it will give us an accurate measurement of the dust mass. And by looking at larger and larger samples, we can then essentially infer properties about the disk dust mass evolution. Then another concept of the disk evolution is essentially the evolution of the gas rather than the dust. The problem is that the gas is a lot harder to study. We rely on various molecules that are difficult to interpret. So I don't want to go into too much detail here due to lack of time, but I do want to mention this sort of big question on two competing theories on how the gas disk actually evolved. There is the classical viscous disk model, which is shown here at the bottom. And this essentially relies on the concept that turbulence drives the accretion onto the star, but that also leads to expansion of the disk and eventually clearing by photoevaporation of, due to radiation of the star, that then clears the disk from the inside out. On the other hand, there is this MHD disk wind model, where the accretion is driven by magnetospheric accretion. In that case, the turbulence is very low, but you do expect to see this magnetothermal wind, essentially a very strong wind, originating from the inner part of the disk. And essentially the study of jets and disk winds, which we can trace at centimeter wavelengths, could help to determine which one of these two processes are dominating in the disk evolution process. So far there has been one very convincing observation of a disk wind, actually taken with ALMA. So this is this rotating CO, this rotating CO wind that you can see over here with these big lobes. Based on the mass loss rate that you can calculate from the CO emission, it was concluded this disk wind must be consistent with an MHD disk wind, not photoevaporation. So that, at least for this disk, that kind of answers the question. The problem is that this is really the brightest disk that we know, and it's really hard to do this kind of observations with other protoplanetary disks. So essentially we need to find a different way to study disk winds and jets, and the answer to that is indeed in the centimeter regime. Because we already know from essentially spectral index studies that the spectral index of protoplanetary disks flattens when you go to shorter and shorter frequencies. There's this split in the slope where we go from thermal to non-thermal emission. And this is essentially what is predicted from jet models, from free models, where the spectral index becomes close to zero from the optically thin part of the jet. And there is one spatially resolved emission image at 3 centimeter shown for the GML Rigate disk over here. But in general, this kind of studies is still rather limited. There is a really cool result that I want to advertise by my PhD student, Alessia Rota. So the paper is very close to submission, so I expect it to be on arXiv soon. In this study, we looked at the central emission of some of these transition disks, this tiny blob here in the middle, at multiple wavelengths. And what we found is that even though the spectral slope of the outer disk, this outer dust ring, is very steep, is consistent with thermal emission, the inner disk is almost flat, consistent with free emission. So these inner blobs in transition disks can actually help us to resolve free emission from the jets or the disk wind from the contributions of the outer disk. And obviously here, studies in the 10 to 40 gigahertz regime will really help us to get more information about these jets and hopefully tell us more about the disk evolution process. So in the final few minutes, I want to focus a bit on chemistry in star and planet formation. Also in chemistry, we've seen very rapid developments over the last few decades. In this plot that was made by Brad McGuire, we see the number of detected molecules in the universe that has increased over the last few decades. We're up to several hundreds now. And the expectation is that with the ngVLA, we will be able to detect even more species and also more transitions of many of these systems. So radio facilities are really driving the detection of various molecules and the properties that we can derive from them. And this is interesting not only from the idea of, oh, a molecule will tell us about the possibility of life, but chemistry can also be used as a physical tracer. And in this overview paper, we see that the different molecules are sensitive to different conditions in these protostellar systems, like the outflows, the cavity walls, the inner envelope, the disk, where we have different temperatures and densities and therefore different molecules that we can observe. So essentially, the more molecules we discover, the more possibilities, the more tools we have to understand the conditions and study the physical processes here. And what is so interesting is that, yeah, it says here I still have 6 minutes, but oh yeah. And what is so interesting about protostars, with all these different components, so the envelopes, the jets, the disks, is that you actually have this wide range of physical properties that lead to different chemical processes. Like, for example, freeze out onto dust grains, but then also thermal sublimation and non-thermal sublimation of the icy layers that enrich the chemistry of the disk. But also shock features that can release other molecules and even create molecules that otherwise wouldn't even have been formed. And we've already seen that in ALMA spectra of several of these protostars, that they show a very rich chemical complexity. And one of the main questions in this field is what happens with the chemical complexity as the system evolves? Where do all those molecules go? Are they reset when essentially when all the material gets locked up in the disk, or do they survive and eventually end up on the planets? And there was a recent result by Tobin et al. Where they were able to measure the H2O over H2O ratio, so deuterated water, for a protoplanetary disk shown over here. And what they found is that the ratio is actually very similar all the way from class 0 protostars to disks to comets in our solar system. So their conclusion is that, yeah, whatever is formed in the protostars survives somehow and then eventually ends up on the planet. So this was a very important discovery. Another range of discoveries that we've started to make is the detection of complex organic molecules like methanol and others located in some of these protoplanetary disks, where these molecules can only be produced by ice chemistry. The idea here is that the icy layers on the dust grains drift inwards to these dust traps, these dust rings, and because the dust rings are located so close to the host star that they can thermally sublimate, we can then observe these molecules again in the gas phase with ALMA. The problem is, and we've seen that in essentially larger chemical surveys of protoplanetary disk, is that whenever the continuum is very bright, there you start to see this decrease of molecular line emission. So we see it over here, like this, the continuum emission, and we see that the molecular line emission gets close to 0. So it's essentially the continuum optical depth is limiting what we can see in terms of molecular line emission, and that means that we're still really lacking information, in particular in the disk stage. So again, by going to optically thin wavelengths, we will be able to study molecules throughout disk evolution without these continuum optical depth issues. So with that, I think I'm just going to leave up my summary for all the, here I'm listing all the different opportunities that I've mentioned during my talk, and I'm happy to take your questions. Thank you very much.
Okay, questions for Nienke? And by the way, we are also monitoring the Slack, so if you are feeling too shy to ask in person, you can ask it. Somebody who's not shy, clearly.
Nice talk. You talked about the dust going away and making planets. Do I need to make planets, or do I just need to make big objects, like bigger objects than dust, right? I need to keep them around, so I can't let it all disappear, but how big do I need to get it so that you've lost it?
Well, the problem is that that we just don't know, right? We cannot measure the dust beyond sort of centimeter wavelengths, and therefore we don't know what's going on. Over there, we're entirely relying on models. So we rely on what we can observe.
Nice talk, Nienke. So in class 2 disks, I think the consensus now is structures are common among at least a large disks bigger than a few tens of AU. Do we know if that's true for class 0 and class 1?
So in class 0 and class 1, there are not really good statistics yet. Also, there we are in a way even more limited to brighter objects. So no, I don't think it's known about like what is the fraction of disk with large scale structure in that in those systems. No.
Thanks.
Okay, other questions? Okay, so we'll continue. Let's thank our speaker.
Yeah, thank you.